Hi, welcome to a short presentation for our work named Affection, Learning Affective Explanations for Real-World Visual Data. This work makes three key contributions. First, it introduces the problem of deep learning affective explanations for real-world images. Second, it publishes a carefully curated multimodal dataset to establish new methods for this problem. And third, it explores the first neural captioning methods for affective explanations in the wild. Typically, established captioning data and underlying models focus on objective visual details that are present in images. For instance, they focus on animate or inanimate objects present in images, object-to-object interactions, etc. However, humans also imagine, feel, and make a variety of associations when exposed to real-world images. For instance, one might imagine the warmth and joy as a parent taking their kids to this water park, or one can feel the anticipation of this air flight returning someone back to their home. To collect such affective captions and build the affection dataset, we follow the protocol of recent affective studies done for image paintings such as Artemis. Namely, we show human annotators real-world images and ask them two key questions. First, to indicate their dominant emotion upon observing an image, and then to further provide a written explanation justifying that selection. In this process, we recruit more than 6,000 annotators living in countries where English is the main spoken language and collect responses covering 85,000 images. The displayed images are taken from 5 popular research datasets with rich meta-annotations. In total, we curate this way more than 500,000 emotion labels and corresponding explanations, creating a rich and complex affective dataset. For instance, these are examples of annotated images, for which in its derived explanation the word bird is used. First, it is worth pointing out that different emotions were justified for its image, despite that the bird entity was part of the explanation, highlighting the emotional variability and deeply contextual grounding taking place in affection. Next, it is also true that in affection the explanations commonly carry sentiment-based and psychological reasoning. For instance, the improbable and imaginative situation of birds popping balloons can be thought as amusing, but caged birds might provoke a sense of anger since they are not in their natural environment. Also, in affection, metaphors, abstractions, and associations based on derivations that are not directly visible in the images are commonplace. For instance, in this image, the annotator attributes the human quality of a solitary walk to this bird. And here, they imagine a paraglider flying like a bird soaring through the sky. Moving on to the last but extremely important property of affection and affective explanations in general, our explanations are intrinsically personal and hence they are subjective. For instance, the charging bull statue of Wall Street can be awe-inspiring to someone associating with the positive qualities of capitalism, or can trigger excitement by inspiring the desire to travel in a place like New York. This phenomenon well explains why 50% of the annotated images have received at least one positive and one negative emotion at the same time. Having established that affection is a complex and rich dataset, we now ask if we can devise deep learning methods to learn its key properties. We propose to do so by breaking the learning-based questions into 3 sections. For our first task, we saw that we can learn its categorical emotion labels. Namely, an LSTM-based text classifier applied on our explanations is accurate in predicting the underlying 9-way emotion labels about 70% of the time, while a transformer-based BERT model performs about 3% better for this task. Similarly, and when associating every image to the emotion label of the majority of its annotators, a simple ResNet can guess approximately 60% of the time correctly the underlying label. Crucially, for both tasks, their binary simplification, where the 9 emotion classes are simplified to positive versus negative sentiments, give rise to classifiers that achieve significantly better performance. For our second task, we investigate the extent to which our affective captions are also discriminative for their underlying images. To answer this question, we use a clip model and find that such a network, without ever being fine-tuned on affection, can still successfully identify images from their underlying affective captions. When we input to clip the ground truth image caption pair and try to confuse this model with random distracting images, clip still reports the highest similarity between the ground truth image text pair, even when the number of distracting images is as high as 10. In other words, our captions appear to have a good amount of pragmatic details describing their underlying images, a fact we will soon use. For our third learning-based application, we propose the task of captioning real-world images with affective explanations. We dub this task as Affective Explanation Captioning, or in short, AEC. This slide showcases a high-level overview of a typical captioning deep learning-based system. An image encoder captures visual features of the input image, and a language encoder uses them to ground itself, say with a transformer or an LSTM cell, and further, via teacher force, learn the distribution of valid sentences represented as a series of tokens. At inference time, once the architecture is grounded with the input image, we can use a likelihood-based sampler to extract a caption with high compatibility with the input image. In our work, crucially, to smoothly introduce AEC and establish simple but also robust baselines, we do minimal changes to this paradigm. Specifically, we first add at the input stage a separate encoder to encapsulate the emotion an explanation is justifying, so as to make for an emotion-grounded architectural variant. And secondly, and by exploring the fact that affection contains pragmatic captions at inference time, we do a few adaptations. First, after we ground the network with a deduced emotion as shown in step 1, and this time sample several likely explanations, as shown in step 2, we are going to rank these samples according to, say, a clip model, shown in step 3, before we output the single caption with the highest clip compatibility with the underlying image. This strategy makes for what we call a pragmatic captioning variant. Here are examples of predicted captions with an emotion-grounded architecture. The left image primarily reflects a positive emotion according to a separately trained emotion classifier, while the right one is more likely associated with a negative emotion. As shown with our captions, our systems go beyond just learning the most likely emotion underlying an image, and instead they further give information as to why that might be. For instance, a person might feel content when making a meal in a tidy kitchen, but also disgusted when exposed to a demolished toilet. Moreover, we can use an emotionally grounded captioning system to alter the nature of its produced explanation by giving to it inputs of emotions that they are distinct for the same image. For instance, here, to justify an awe-inspired reaction, our system focuses on how one could see giraffes in person when they are kept in a zoo, and on the opposite side, how one can feel sad for the fact that such magnificent animals are enclosed in an artificial environment. Different from the previously shown effects of emotional grounding, here we highlight the effect of turning a vanilla architecture into a pragmatic one by showcasing a prototypical example. To the left, we observe a relatively dull caption given by the vanilla architecture for the shown image. However, the pragmatic explanation to the right not only is more sound to justify an emotional reaction, but here it also corrects the grounding visual details, since this shown photo is indeed taken inside an airport and not a bus station. We close our study by quantitatively exploring the effect of architectural variants against a large variety of captioning metrics. In summary, we make the following observations. First, newer metrics that are reference-free, i.e. they do not rely on ground truth captions in test sets, but use clip to measure the compatibility of a caption and an image, significantly favor our pragmatic variants. Second, the pragmatic variants also tend to create generations that are more diverse across a set of images, i.e. they suffer from less mode collapse. Last, the emotion-grounded variants do best on specialized and affect-oriented metrics, like those introduced in recent previous works, which, for instance, capture the emotion compatibility of the generated captions and the underlying image. One last metric we'll use here is based on a human study imitating a Turing test. Here, annotators were asked to select among a generated caption and a human-given explanation and decide which one was the most possible to be given by another human. Importantly, in this study, all our captioning variants fare extremely well, namely 60% of the time or more. The judges found that the generated captions were at least as likely as to be given from actual humans. Of course, despite our initial success in the AEC problem, much future work is needed. We need methods and metrics that better understand things ranging from the simple objective details portrayed in input images to the much subtler emotional implications such details might have, not just for one person, but ideally for an entire population. For many more details, including affections data, please visit our project's webpage, or if you are at CVPR, please visit our poster. Thanks for listening.